Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and today we're going to be talking about adiabatic processes. Basically, we're going to be talking a lot about air parcels, how they move, and how that movement through vertical processes, lifting processes, impacts air temperature and humidity. So let's go ahead and dive into it. So in the last video, we talked about a variety of different humidity indices or measures. Specific humidity, which is just the mass of water vapor per unit mass of air, including the water vapor itself, grams per kilogram. Mixing ratio was the mass of water vapor in a unit mass of dry air. Vapor pressure was the part of the total atmospheric pressure attributable to its water vapor content. Relative humidity is the ratio of actual water vapor content of air to what the water vapor content would be if the air was saturated. And dew point is the temperature at which air, given its vapor pressure, would become saturated or would be saturated. So that's just a recap from what we were talking about in the last video. Now this video is going to focus, as I said, on adiabatic processes. Now there are two different forms of processes here at work that correspond to how air is cooled to its dew point: diabatic processes and adiabatic processes. Through these processes, condensation or deposition occurs. Diabatic processes are any temperature change of air that is not related to its adiabatic vertical displacement. Adiabatic processes deal with the changing temperature of a parcel of air due to air rising or sinking adiabatically. Adiabatic processes assume that no heat, mass, or momentum pass across the air parcel boundary. Rates of adiabatic change occur differently depending on whether or not the parcel of air is saturated or unsaturated. We'll talk a little bit about that in a number of slides here. But first, let's go ahead and think about clouds very briefly. There's going to be an entire lecture, multiple lectures on clouds in the next week or two. So we're just going to kind of ease our way into clouds. Clouds are just collections of atmospheric water particulates. Those particulates are typically a radius of around 10 micrometers. They consist of liquid or water droplets, solid or ice crystals, or some combination therein. They can form by condensation or deposition within the atmosphere, typically around some type of seed particle or seed nucleus, essentially. Clouds can form when air becomes saturated via adding water vapor to it, mixing cold air with moist warm air, or cooling air to its dew point. And that's the big one that we're going to focus on today, is cooling air down to its dew point, or in this, lifting and adiabatic processes. So that's what this video is going to focus on. So let's pretend that we have some type of process happening there. So adiabatic processes, we're thinking of just air lifting, right? So here we are on the surface. We know that air pressure decreases with altitude, and with that decrease, our parcel of air expands. We can see it getting bigger and bigger and bigger here. Likewise, as it falls, it increases in pressure, decreases in area. So that air parcel condenses. If we have an unsaturated parcel of air, that is changing at what we call the dry adiabatic lapse rate, or DALR. Now, the distinction here, and the key distinction, is that if air is unsaturated, it moves at the dry adiabatic lapse rate. It just has to be below 100%. 100% relative humidity. If it's at 100% relative humidity, it is fully saturated, and then you use the saturated adiabatic lapse rate, which we'll talk about here in a second. But until that point, it is dry or unsaturated is what we consider it. So you will be using, if you're calculating this, the dry adiabatic lapse rate to figure out the rate at which air cools as it rises. Now that rate is more or less understood. It varies, obviously, as all things do in science, but we can kind of estimate, on average, the dry adiabatic lapse rate is a change in about 1 degree Celsius for every 100 meters, or 10 degrees Celsius per every kilometer, the air parcel rises into the atmosphere. So, if we were looking at an example, here, for example, we have our cloud formation occurring at a certain point. We'll see where that is. But we have an air parcel where our temperature within the air parcel is 35 degrees Celsius. The dew point is 25 degrees Celsius. So if we think about that dry adiabatic lapse rate that we just talked about, that says that for the air temperature to cool to the dew point, you need to decrease 10 degrees. And if you are decreasing 1 degree Celsius every 100 meters, that tells us that we need to rise 1,000 meters or 1 kilometer into the atmosphere before our air parcel temperature cools down to our dew point temperature. So let's go ahead and take a look at that here. So here we go. At 500 meters, our dew point is 25 degrees Celsius. Our parcel of our air temperature of our parcel, is 30 degrees Celsius. By 100 meters, or sorry, 1,000 meters, we've cooled, again, 5 more degrees. At that constant rate of 1 degree Celsius for every 100 meters, we are now at our dew point. And we know that when our air temperature is equal to our dew point, we have fully saturated air. Now, this point is what we call the lifting condensation level. And that's just the height at which the rising air is cooling at the dry adiabatic lapse rate, becomes saturated, and condensation begins. What do you see that as? Well, you see it as the bottom of a cloud or the bottom of a bank of clouds. That's what our lifting condensation level is. It is the base of all these little clouds that we see here, even all the way into the distance. They're all at about the same altitude. So, simply put, we can say that the dry adiabatic lapse rate of 1 degree Celsius for every 100 meters allows our air parcel to cool 10 degrees by the time it hits 1,000 meters or 1 kilometer. Now, we add, because this is a 300 level course, the difficulty. Dew point does not stay the same as you rise. It also changes. So let's look at here. We ask the question, what happens to air pressure in a parcel as it rises? Well, it decreases, right? What then happens to the partial pressure of each gas in a parcel as it rises? So if we look at our initial dew point of 25 degrees Celsius, if we know that our pressure is changing, that air parcel is expanding, that dew point's going to have to change as well. At 500 meters, air pressure is 5.5% less than it was at the surface. So our initial vapor pressure might have been 31.7 millibars, but at 500 meters, we're taking 5.5% off of that, and we have 30 millibars. So we lose 1.7 millibars. So we can see here, by the time we get up to 500 meters, our dew point is 24 degrees Celsius. So that, again, is we will hold as kind of a constant rate. And the quick math you can see here is if you rise, if you're going 500 meters up and we had a full degree of Celsius of change, well, the quick math on that is about 0.2 degrees Celsius for every 100 meters. And that's kind of what it comes out to be. So let's rectify this a little bit. What's our dew point? If we know that rather than being 25 degrees Celsius is the dew point here originally was, it's now 24 degrees Celsius because it has dropped 0.2 degrees Celsius for every 100 meters. What would it be up here? At that same rate, we're going to hold that rate constant. So by the time you get up another 500 meters, that says we'll have cooled 5 times 0.2 again. A whole nother degree. Now we call that our dew point lapse rate, or DPLR. And the dew point lapse rate, again, just comes out to be roughly 0.2 degrees Celsius for every 100 meters of rise. That says that our dew point and air temperature at 1,000 meters still aren't the same thing. So we haven't hit our lifting condensation level yet. So we have to figure out, how do you actually account for two variables changing at the same time. Well, let's figure that out a little bit. So here, that parcel's going to change, and the kind of crossing point between the changing air temperature and the changing dew point is going to be right here at about 22.5 degrees Celsius at 1,250 meters. So if we take our dry adiabatic lapse rate, 1 degree Celsius for every 100 meters, and our dew point lapse rate, 0.2 degrees Celsius for every 100 meters, we can come up with this nifty little equation here that says that the height of the lifting condensation level is equal to the air temperature at the surface minus the dew point at the surface. So here, air temperature at the surface, we could say, sketch this out. Apologize, I'm writing this with a mouse. So we've got our air temperature. This is AT at surface. And then our dew point at the surface, this is here, dP surface. That just gives us a difference of 10 degrees C, right? Easy math here. You divide that 10 by 0.8 degrees C for every 100 meters. And that's going to tell you the temperature at which you are going to meet the height of your lifting condensation level. So continue on here. I've got another couple of things to show you. You could also come up with it like this. You could do air temperature at the surface minus your dew point at the surface divided by 0.8 degrees Celsius times 100 meters. You can kind of do them depending on your purpose. You can do them with either of those equations. So we've hit the dew or the lifting condensation level, right? It's 1,250 meters. Air is fully saturated. Our relative humidity, RH, is equal to 100%. Right here. Right at our lifting condensation level. Now, when you have air at saturation, 100% relative humidity, you have to switch gears, and you're not using the dry adiabatic lapse rate any longer. And you're also not using the dew point lapse rate any longer, because a couple things happen. First off, your dew point and your air temperature are going to change at the exact same rate so long as you're at saturation. We'll figure out when you're not at saturation here in the next part of the example. But for these purposes, once you hit that lifting condensation level, any rise in that air parcel, the air temperature and the dew point are going to change at the exact same rate. That's very important, because if they don't, then they're not going to be saturated anymore. But as air is rising, it will continue to be saturated until it starts to decrease in altitude again. We'll talk about that here. But for the next part of the equation, here we're going to rise from 1,250 meters to 1,500 meters. What's going to be the parcel air temperature and the dew point air temperature? Well, for that, we use our saturated adiabatic lapse rate, or SALR, because this is all still within the cloud cover here. So we're still at 100% saturation, right? Well, this is not as easy or as cut dry, we'll say, because this rate is variable. Now, we're going to hold it constant whenever we have a given example, but just know that it varies somewhere between 0.4 and 0.9 degrees Celsius for every 100 meters, and that's dependent on a lot of different factors. But this is the rate, somewhere between 0.4 and 0.9 is the rate at which air is cooling for every 100 meters of rise while it's saturated. So in this example, we're going to say that our saturated adiabatic lapse rate is going to be 0.5 degrees Celsius for every 100 meters. And we are rising 250 meters, right? So some quick math. That says that our air temperature is going to decrease to 21.25 degrees Celsius. And if you're playing along at home, think what that dew point's going to be, right? It's going to change at the exact same rate. So it's also going to be 21.25 degrees Celsius. So what happens then when that parcel starts to decrease in altitude for some reason? Well, a couple things happen. We assume, now, again, nuance of trying to understand this at a rudimentary level, we assume that the second your air parcel starts to decrease in altitude, immediately you are unsaturated, using the terrifying air quotes, unsaturated. And that lets us say, okay, air parcel is no longer saturated. We can revert back to using the dry adiabatic lapse rate and the dew point lapse rate to calculate the increase in temperature as that parcel of air drops back down to the surface of our planet. So what does that look like? As we are going from here to here. So again, descending air warms, we'll assume AT and DP are immediately different, back to using our dry adiabatic lapse rate and our dew point lapse rate. That says that our parcel air temperature and dew point are going to equal, pause for effect. Go ahead and pause the video here if you're trying to work it out. So basically you're going to look at that elevation or that altitudinal difference, so 1,500 meters. So it drops 1,500 meters from altitude to the surface. So it's warming that. If you just take that dry adiabatic lapse rate and say, 1,500 times, or 1,500 meters, we'll say, so we'll do that here just for an example. So 1,500 meters times 1 degrees Celsius for every 100 meters. Meters are going to cancel out. We can cancel those out. That's basically going to say that you have 15 degrees Celsius of warming. So that says that we're going from 21.5 degrees Celsius to 36.25 degrees Celsius, right? You can do the same thing for the dew point because that is warming at 0.2 degrees Celsius for every 100 meters. So that would give you 24.25 degrees Celsius. Notice they're slightly different. We're slightly warmer and the dew point is slightly colder. So here we're drier. The air parcel is drier at this point than it was when we started our journey. So just as a kind of recap, so this is important. You've got your lapse rate. So as parcel of airs rise, they cool at a lapse rate. The rate of temperature change with height. That's all a lapse rate is. The dry adiabatic lapse rate is for unsaturated parcels that cool at a rate of 1 degree Celsius for every 100 meters. The saturated or moist, you can use them interchangeably, adiabatic lapse rate is somewhere between 0.4 and 0.9 depending on your conditions. Then you've got your dew point lapse rate, or DPLR, that cools or warms at a rate of 0.2 degrees Celsius for every 100 meters. Now the dry and the dew point lapse rates you use when you have an unsaturated parcel of air. The moist adiabatic lapse rate is when air is fully saturated at a relative humidity of 100%. Now, we will introduce another lapse rate, the environmental lapse rate, which is basically the change in conditions completely around and encompassing that air parcel. We'll talk about that a little bit as we dive into the nuances of atmospheric stability, which is very important for considering how air parcels move and how storms can develop. So we'll dive into that in the next lecture, but until then, I hope you have a great day and we'll see you in the next one. Thank you.